So we talked about phase diagrams for copper and silver. We talked a lot about phase diagrams and the different microstructures we'll see based upon the composition and the temperature where it exists in the phase diagram. And we talked about the lever rule and how to calculate the fractional amount of different phases based upon the where it exists in the phase diagram. So in this lab, we are going to do two main tests. We're going to do a micro hardness test on our samples. So we talked about solid solution strengthening at the end of the lecture, and a good way to tell the effect of this strengthening is through a micro hardness test. So we are going to take our samples and we're going to use the Knoop indenter this time as opposed to the Vickers. If you remember, Knoop is the elongated diamond indenter, but we still use the same hardness machine to do it. And we are going to make indents in the sample in our alpha region, our alpha phase. We're going to do it in our beta phase, and we're going to do it in our eutectic phase, which you remember is a layered structure of alpha plus beta. And along with that, we're also going to do indents in a pure copper phase, so 100% copper, and a pure silver, so 100% silver. Alpha and beta, you might remember, is not pure copper and pure silver. It is just copper and silver with the other one dissolved into it. So it still maintains the same crystal structure as the base material, but now other metals, the secondary metal is dissolved into it either through substitutional solution or interstitial solution strengthening. So I'm just going to walk you through one indent on the Knoop indenter. It's going to look very familiar as the Vickers test. And then we're going to go to the microscope, and what we're going to do for the lab is we're going to give you a few different alloyed samples. So in these boxes here, you see we have a bunch of pre-prep samples, and each of these are labeled with a letter and a number, like A1 through A9 and B1 through B9. And the goal of this is to take the microstructure that we see, and we figure out the percentage of each phase present. And by doing that in a image analysis software called ImageJ, which is free, we should be able to figure out compositions, at least get relatively close to the actual composition of our material. And then in the next lab, we're going to do EDS spectroscopy with the SEM, which will tell us very, very accurately what the composition is. So what I'm going to do is I'm going to do one Knoop indent just to show you how it's done and talk you through it. And then we're going to go to the microscope right behind the camera, and we're just going to look at the different phases just to kind of show you that the microstructure can be different even for all of our copper, silver alloys. And then I'm going to go over to my laptop and we're going to show you how to use ImageJ to calculate a rough fractional amount of different phases in the system. So let's do the Knoop indenter. So the machine works the exact same as it did before. If you remember, we have our optic and indenter heads that rotate, and by switching between them, we can switch between a 10x, a 20x, and a 40x objective. We can also switch between a Knoop indenter and a Vickers diamond indenter. So I'm going to bring the camera over. So we still have our tablet over here on the right. It's going to ask us to zero the eyepiece. So unlike in the first lab, we were measuring A and C, our crack lengths for our system. Here, we're just calculating Knoop hardness. So we can use this machine to directly measure the diagonal. In the material science handbook, in the same section where they talk about hardness tests, they tell you how to calculate a Knoop hardness. It is, it's like 14.2 multiplied by P divided by the longest diagonal squared. Feel free, please check that on your own time. Don't trust me that it's exactly that. So, but because we're not calculating crack length at all, we're just measuring the diagonals, we can actually calculate hardness with the machine itself. and that would give us hardness values, which would, if you were doing this experiment, really speeds up the time because you don't have to take your sample over to the optical microscope to measure the crack length. So the first thing we have to do is we have to set the system up, and you may not be able to read it, but it's saying we need to zero the filler eyepiece. So the way that we calculate that, the diagonal, are these two knobs on our system here. They move a series of lines in our sample, and you basically move the lines until one end is at one end of the diagonal and the other is at the other end of the diagonal, and the system measures that distance, and then we'll calculate the hardness for you. So I'm going to zero the eyepiece real quick. Okay, now it says we are ready for indent or measure. See, this is a previous test of 84. You can hopefully see on the top we have switched to, if we go to menu, scale. So you can now see we have switched to a Knoop indenter, and we are indenting with 1,000 grams force, so 1 kilogram, the same as we did for our Vickers. And we are going to indent for 10 seconds, it says right here. So I'm going to take my sample, which in this case is this puck here, and mount it on the stage. Take our puck and we slide it in, and then we tighten our grips, we raise the stage, so I'm going to now move the stage. So now I'm going to move the stage up and down to get it in focus in the objective, in the 20x objective, and then I'll switch to the Knoop indenter and perform the test. And this sample is a relatively old sample. It has been used throughout the years repeatedly. So it has a lot of previous indents already in it. So it's important to remember about the Rockwell test, and this applies to the microhardness test as well, that you don't want to indent close to a previous indentation, because indenting a sample cold works the sample in the immediate surrounding volume of material. So our sample is slightly harder near the area where indent occurred. So you want to make sure that you find your indent location, and it's far away enough from other samples. Generally, for the Rockwell, they said at least 3 indent diameters away from the indentation. Vickers, I don't know if there is an exact scale for how far away you need to be, but generally I just move the old indent off the view screen and go to a new place of unindented material. I found a clean location with no indents, and I have it in focus now, so I'm going to turn it to our Knoop indenter, and I'm going to go ahead and hit the start button. So our test is completed. It's really quick. Now it is asking for a diagonal in microns. You might remember when we did the Vickers test previously, it asked for 2 diagonals, because with Vickers you take, because it is a uniform diamond shape, you take the horizontal and vertical diagonal of your diamond, whereas for the Knoop you only take the diagonal of the longest dimension of your indent. So it only needs 1 to calculate a Vickers hardness value. So now I'm going to use these 2 knobs that I zeroed at the beginning of the test to put them on the edge of my diamond on both sides, and then I go ahead and hit the button, and it measures that distance, and then it should give me a Knoop hardness value. So I'm going to go ahead and do that. So I have matched up the diagonals to the length of my sample, and I'm going to go ahead and hit the button. And hopefully you can read that. It says our diagonal length is 435 micrometers, and that gives us a Knoop value of 75. So we have done that for one sample, and I didn't actually check. This sample's pretty messed up, so I can't really tell what the microstructure is, but in the regular lab, you would the samples would be polished ahead of time, and telling the microstructure is relatively easy. So in this case, in the actual lab when we did it, we would take hardness tests on the, as I mentioned, a pure copper sample, a alpha sample, which is copper and silver, but mostly copper, a eutectic sample, remember, which is layered alpha and beta, a beta sample, which is silver and copper, but mostly silver, and then a pure silver sample. And you compare all those Knoop hardness values to each other. And I'm going to provide those values to you, and so that way you can see the difference in Knoop hardness with different amounts of strengthening. So we talked about that. We expect that our lamellar structure might be slightly stronger than our base materials because it has the two-part strengthening of our layered sample, kind of like our composites. So you can see if that's true in the case of our materials. So we did our Knoop hardness. Now the second part of the lab requires using the optical microscope to get microstructure images of our different unknown samples. So we're going to go to the microscope right behind me, or right behind the camera, and I'm going to pick 3 samples, and we're going to look at the microstructure mostly to show you that even though they're all copper silver, we can get very, very different microstructures. So let's go over to the computer. So I have chosen 4 unknown copper silver samples. They all look something like this. You see they're a little beat up. They have some scratches on them from older semesters, but I have repolished them a little bit, so hopefully we can see the microstructure fairly easily. So what we're going to do is we're just going to look at the camera and see the difference in microstructure. They're all copper silver, but they all exist at different points on the phase diagram, different compositions. So we're just going to go through them, and I'll kind of point out the key features that you should look for when looking at the microstructure images on canvas. And so let's turn over to the camera. So right now there's nothing on the screen. It's blue because there's nothing in front of the optic. So I'm going to go ahead and put the sample in front of the optic, and this is for this is at 20 times magnification. And actually, while we're here, we do see something interesting. Let's get it in focus. So we mounted our sample in these phenolic resin pucks, these kind of green pucks, and under microscope, this is what they look like. This kind of black, wavy, amorphous goop. So in the future, when you're ever looking at samples in the microscope, if you see something that looks kind of like this, know that you're not looking at your sample. You're looking at the plastic that holds your sample. So you need to move elsewhere. And luckily, our sample is down here. So let's move the sample. Here is an old Knoop test. So when I was measuring the diagonal of my sample, I was measuring the distance from this point to this point. So we see, let's move away from the Knoop just to get kind of nice microstructure. There we go. So in this image, there's a few things you can probably see. So we have our kind of orange background, which is the vast majority of this picture. So this would be our copper matrix, our copper alpha phase. And then in between the copper phase, we have these little regions of silver. And this would be our beta phase. So we have a large copper matrix and a very small silver matrix, which, if you think about its position on the phase diagram, this is probably pretty far to the left of on the phase diagram to a low silver composition, because most of our copper solidified before our silver solidified. So this is at 20 times magnification. We can zoom in and go to 50 times. And if we zoom in, we see our silver features a little bit more, and I actually forgot the most important thing, which is the scale bar. And added our scale bar here. So this is our 50 micron scale bar. So these phases are well below 50 microns, some of them, as thin as 5 microns thick. So lots of copper, very little silver. So that's just one option for phases. So let's go back to our 20x. I'm now going to go on the other side of the phase diagram. So we just looked at this guy, kind of orangish. Now we're going to look at this guy, which is much more silver. So we're going to go ahead and pop that on there. And our scale bar is no longer accurate. So this is a much different microstructure. You see we have lots of this silver background. So this is our beta matrix. And inside we actually have this orange matrix, which when you look at it, looks like probably just alpha. But that is why we take magnifications at two different magnifications. We take one at 20 and one at 50. So let's zoom into 50. And at 50, we actually see that this is a eutectic phase. Hopefully you can see we have a layered structure, kind of layers of silver and copper mixed together. And it's over here as well. And if we move around the sample a little bit, oh, yeah, there you go. It's very prominent there. So here we have our beta phase and our silver, and a very, very noticeable alpha plus beta eutectic phase. So this is probably closer to the center of the sample because we have a larger volume of material that was able to form eutectic compared to in the first image, where we had a very, very small amount of material that was able to precipitate out of the base. Okay, and now we'll go to our third sample. And our third sample, we're at 20x. And our third sample is very interesting. This is actually looks like a very uniform microstructure, or at least very evenly matched. We have a large amount of copper alpha phase, and we also have what looks like mostly silver, but if we zoom in, we can see that this is actually a eutectic alpha plus beta phase as well. So this is 20x. So now let's go to 50x. There we go, and the eutectic is much more visible now. We still have our our base alpha phase, our copper phase, and our very nice eutectic of copper plus silver, or alpha plus beta. So because we have a lot more base alpha, we expect that this is closer to the copper side of the phase diagram than the silver side compared to our previous sample. So lots of different phases we can get. And there's one more sample that I would like to look at. Able to see it's a little messy, but we do see some eutectic and some kind of darker shades here. So it's definitely mostly eutectic, and we have this kind of matrix, and this is at 20x, but when we zoom in to 50x, we see that it's actually all eutectic. This whole thing is eutectic, from the big phases to even this guy on the side. This entire sample has our layered structure. So this is this would be a pretty good guess to say you can guess the composition of this sample, because we have very little pure alpha and pure beta, and we have almost entirely pure eutectic in our sample. So we saw lots of very, very cool things under the microscope about our samples, and microscopy is probably one of my favorite parts of doing research and being a scientist and being a teacher, because it allows you to see worlds that cannot exist in your eyeball. You need tools to see them, and you see amazing things sometimes. And this is just optical microscopy. It gets even crazier when we move on to scanning electron microscopy. So more cool things are in store. But as we saw, we have our 4 samples. Can't see them all. Our 4 samples. They all look relatively similar from a eyeball point of view, from a macro scale. But when we zoom in, we see we can have very, very different microstructures just based upon the composition of our sample. And these microstructures will define our material properties and will define how our sample is going to handle different stresses in different situations. So controlling the microstructure is really important, and to do that you need to understand the phase diagrams. So that is why we talked about the phase diagrams, because they're useful for knowing what your sample is going to look like. And everything happens, all deformation happens at a micro scale and eventually moves up to macro scale. So you have to know what the micro looks like to understand what happens at the macro level. So there's going to be both low and high magnification images for different samples posted on Canvas. The idea is your group is going to take 3 of those samples, and they are going to use ImageJ to calculate a fractional amount of each phase in your material, and then from there you're going to report that value, and hopefully we can see if our microstructure images match up to what we would expect to find in the phase diagram. So I'm going to kind of walk you through how to do one of these ImageJ adjustments. There is a document on the Canvas page, there will be, that will walk you through it. It's very, very easy, but we can go over, let's go over to my laptop, and I will just walk you through how to take a fractional image data from our different microstructures to figure out alpha and beta phases. So I'm at my computer now, and I have got some of the images that we just showed you in the optical microscopes. I have one saved to my desktop. We have image B8 right here at 50 times magnification. So in order to do this threshold analysis software, we're going to open ImageJ, which you can download offline for free. It is a very popular image analysis tool. And what we're going to do is we're going to open that file. So B850. This is the file. Hopefully it fits on screen. And in order to analyze the area fraction of each of these components, this is most likely our silver beta, and we have a eutectic alpha plus beta region here with our copper as our alpha. We need to first turn this image into a format that ImageJ can read, and to do that, we need to convert it to a black and white image. So we're going to go to Image, we're going to go to Type, and right now it's a RGB color image. We're going to turn it to an 8-bit, which will turn it black and white, or I guess gray and white. And then we need to basically set a threshold to say anything below this color is going to be beta, and anything above this color is going to be alpha. So to do that, we go to Image, Adjust, and Threshold, or Control-Shift-T. And as you can see, it turns our image black and white and gives us this little region where it defines what it thinks is the best match. You can slide these guys back and forth to increase and decrease the range that it measures over. So I'm going to try to just get eutectic, and if you go too far, then you lose the eutectic, but if you go the other way, everything becomes black and it becomes difficult to see. So there's a little bit of wiggle room. It's not really an exact science. This is just kind of to get you in the general region of where you think your sample is going to be composition-wise. So I'm pretty happy with that. I'm going to go ahead and hit Apply. I'm going to close this. And then to figure out the ratio between these two, I'm going to go to Analyze, and I'm going to click, I'm going to go ahead and go to, I need to measure, but first I'm going to set measurements, and this window will come up, and you want to make sure that you have area fraction selected. So it will tell you the fraction of the white to the black. So it's selected right here. Go ahead and hit OK. And now we'll go to Analyze and Measure. And it comes up with this table. And you can learn lots of stuff, but what we care about is the percent area. So in this image, this would be the percent of white. So the percent of beta in our image, because you remember this part was lighter colored. This is our silver beta region. So now we know we can say the area fraction is 80.6% beta and 19.4% alpha. And we have to make an assumption here. We're going to say that we're going to assume that our area fraction is representative of our volumetric fraction of our sample. So we're going to say that the volume fraction is the same as our area fraction. Now that we have that 80.6 and 19.4, we need to figure out the mass of each of these guys. So to do that, we need to figure out a density for each of them, so we can multiply our volume fraction by our density. And to do that, we go over to this handy dandy handout, which is going to be up on Canvas. And so in another image, they calculated 90 and 9%. And we need to calculate the density of our alpha beta phase, so we can multiply it by our volume fraction. So to calculate a density, we need to know the composition of our alpha beta phase, and we know that we are below the eutectic point where everything solidifies. So we're going to say that at the eutectic point, alpha has a maximum silver concentration of 8%, and beta has a maximum silver concentration of 91.2%. So those will be our kind of, those are the ends of our tie line. So we can do, say that our fraction of alpha, so we have, is equal to 8% times, this is the density of silver, minus the density of copper, and we add that to the density of copper. So that is our alpha density. Our beta density is going to be 91.2 times silver minus copper again, plus copper. This is our silver density. And our eutectic density is going to be 71.9 times silver minus copper plus copper again. So this is our eutectic density. So then to calculate the mass of our materials, we need to do the lever rule. So we say if we're looking for the fraction of beta in our image, which is the majority, we can say that our fraction of beta times our density of beta should give us our mass of beta. And then all that is divided by the fraction of alpha times the density of alpha plus the fraction of beta times the density of beta. So we're basically saying our beta weight divided by the weight of all of our material at once. And that gives us a fractional mass of, so in this case it's 91.4. In the other case you would plug in our 80.6 and our 19.4 in these cases here. And from the lever rule we can say that we have an unknown composition, C naught, but now we know our fractional mass, which is in this case 9.14. We plug in our C alpha, we plug in our C beta minus our C alpha. So this is our tie line here. And we would get a, if you work backwards through C naught, you get a fractional composition of silver. So we can say for this sample that they talk about here, it has a composition of roughly 85% silver. So relatively easy. You just need to calculate densities. Well, first you need to take your image and convert it to black and white, then turn out the fraction of each one of your phases. Then you calculate the density for each of those phases. Then you calculate the total mass of your phase present in your image, and then you use the lever rule to calculate the original composition of your sample. So you're going to do that for one or two of your samples, I believe, maybe all three. I don't remember, but relatively easy to do. And you'll report those compositions, those calculated compositions, on your lab report. And then next week we will see how accurate those compositions were, because we will take your sample into the SEM and do EDS spectroscopy, which gives us chemical analysis of our materials. Okay, so that was the lab. We have taken some Knoop hardness tests of our varying copper silver alloy samples. We have looked at their microstructure and seen that varying the amount of copper and silver varies the amount of alpha and beta in our samples, and that of course also varies our microstructure. And we used our ImageJ software to do kind of a quick analysis to help determine or estimate, I guess, our varying composition. So I will see you all next week.